Good evening, everyone. I am Shivani Dhok and I welcome you all for the week 10 tutorial for the course of Modern Digital Communication Techniques. So, let's start with today's session. And like every session, this particular session will be divided into two parts. The first one or the first part will be recap of week 10 content, and followed by we'll have the questions which are related to the content that was covered in this particular week. So let's start with this week's content. You may stop me at any point and ask your queries. I'll be happy to answer them. Let's start with the recap. So, before going ahead with the recap of this week's content, I will like to mention that in the previous week, that is week 9, we focused on optimal decision rules. Like we looked at the maximum likelihood rule and maximum posteriori rule for detection at the receiver end. Now, the next thing that we need to intend to do is understand or evaluate the performance of those particular decision rules. And one of the metric that helps us in doing that is probability of error, or bit error probability, or symbol error probability, as and when the meaning is based on the reference to context what we are talking about. So the in this week we focused on deriving the probability of error for various constellation schemes. So in general, if we understand like if we try to understand what is probability of error is, suppose I have an m point constellation and suppose my transmitter transmits SM and my receiver receives SM hat. Now this probability of error is basically probability that my SM is not equal to SM dash or SM hat. This is in general probability of error, and this probability of error depends on the way we decode or way we detect this SM hat, which means that it largely depends on our decision rule, the decision rule that we are employing to detect at the receiver end. And that's why we need to, if we want to create a proper decision rule, then our aim should be minimizing this probability of error. Now in this week we looked at the probability of error for known constellation schemes, and the very first scheme that we started with was the binary pulse amplitude modulation. This forms some sort of a basic thing because it's just a 2-point constellation with constellation points something like this. Let me draw it anyway. So we have it something like this. This is 0. And binary pulse amplitude modulation, or rather pulse amplitude modulation, is a one-dimensional signal. So I can just write it as basis as ft. This is minus under root es, and this is under root es. So this is basically my s1t, and this corresponds to s2t. So this is what is written here. So s1t is equal to minus s2t equal to gt, and this noise is distributed as a Gaussian random variable with 0 mean and variance and not by 2. And the probability of error for this particular constellation is obtained as Q function of under root 2EB by N naught. So this is the probability of error, where this Q function Q of x is defined as 1 upon under root 2 pi integral x to infinity e power minus t square by 2 dt. And if we want to visualize this Q function, so I'll just take this part here. Yeah. And if we want to visualize this Q function, then it is basically the tail probability of standard normal random variable. So my standard normal random variable looks like this. So this is the PDF where this x is Gaussian with 0 mean and unit variance, and if this is, let's say, x, sorry, let's say this is X, then this region corresponds to probability that my X is greater than X, and this is given by Q function, which is Q of X, and this is also referred as the tail probability. This is just a side information which might be useful in your upcoming courses. After looking at binary PAM signal, we went on to look at the probability of error for M-Array pulse amplitude modulation. So after looking at binary pulse amplitude modulation signal, we looked at the probability of error for M-Array PAM. I'll request you to just tell me if I'm audible and my screen is visible properly. Just a quick feedback in chat box will be fine. Am I audible? Okay, fine, I'll continue. After deriving these equations, we looked at some of the insights that the probability of error curve gave us. So we observed that our probability of error increases with m, and this is for a particular given energy, and the probability of error, like for a given probability of error, we need higher EB as m increases. So the probability of error curves were something like this. So this was EB by N naught in dB, and this is PM, and this was the curve for m equal to 2. Then for m equal to 4 it increased, then for m equal to 16, and so on. So if we look at the given value of probability of error, we require higher value of EB to get the same probability of error as my m increases. And if we look at a particular value of EB, then we observe that as m increases, the probability of error is higher. These are the insights that we obtained. After looking at pulse amplitude modulation, we derived probability of error for M-Array QAM, and for doing this we used the results that are there for pulse amplitude modulation by claiming or by commenting that one QAM, or let's say M QAM, is basically formed by two pulse amplitude modulations, one along in phase phases and another along quadrature phase basis, and both of size under root m. And using this information, we derived the probability of error. So for a constellation size of under root m, the probability of error for this for PAM, 2-array PAM or binary PAM, I'm sorry, under root m square root m array PAM is given by this formula, and the probability of error is 1 minus the correct probability. After that, we found some upper bounds on this probability of errors, which came out to be something like this. Furthermore, we considered we looked at similar insights the way we did for pulse amplitude modulation. We observed something similar happening, that is, as m increases for given energy, we get a higher probability of error. After looking at these, we went on and looked at the probability of error for MPSK. This was just a mention. However, it was not derived. It is a bit complicated derivation. So it was not derived in the lectures. However, it is good to know this formula as well. So this is what we are having here, where this gamma s is average symbol energy by n naught, Es by n naught. And it also has similar trends of probability of error as we observed for pulse amplitude modulation. After doing this, we went on and looked at the probability of error for M-Array orthogonal signaling, and basically we did it for any orthogonal signaling, and we found it to be, we found the probability of error, the symbol error probability, as something like this, and we also derived that this symbol error probability is approximately equal to twice the bit error probability. However, when we looked at the insights for this particular constellation scheme, we found an opposite trend. That is, for a given EB, the PM, the probability of error reduced as M increased. Also, for given probability of error, we required less energy compare as M increased. So complete trend reversal we observed, which was something like this, this was for M equal to 2, then it reduced for M equal to 4, and it further reduced for M equal to 16, and so on. Something like this we observed for orthogonal signaling. And in order to understand how this is happening, or how arbitrarily low can we go, and what are the energy, or what is the minimum amount of energy that we require to have such kind of situation. So for that we looked at the union bound. That is, if we need to find the probability of union of any union of some events, then that probability will be less than or equal to summation of the probability of those particular events. After employing that, we derived a condition or an upper bound on the probability of error for this M-array orthogonal signaling, which came out something like this, and we said that this will tend to 0 as k tends to infinity, but only when this factor, this exponent factor, is greater than 0. Otherwise it will diverge to infinity, which will give us a trivial upper bound. So for that we require EB by n naught to be greater than 2 times log 2. A tighter bound was also looked at, which gave us a condition that if which is valid basically for the case when EB by n naught is less than 4 log 2, and that upper bound was obtained something like this. So if my EB by n naught is greater than log 2, then this probability of error tends to 0. So we can go arbitrarily close to 0. However, we'll need the value of k to be high. If my k is high, then m equal to 2 to the power k will also tend to infinity. This particular thing increases exponentially with k, and it is a very large quantity, and again these are orthogonal signaling, which means will require m basis and will consume a large amount of bandwidth, a huge bandwidth we will consume. So we are trading off our probability of error with the cost of using higher bandwidth, which may not be desirable in many cases. So these are some of the insights that we looked at. After looking at these, we said that okay, now we'll go and look at or start looking at a new concept, which is channel capacity, which was not introduced in that. However, to understand that concept properly, we first looked at different channel models. In that, the first thing that was considered was this binary symmetric channel. So it is evaluated at the binary interface. So what do we have is the two possibilities, or basically many possibilities can also be there, but since it is binary symmetric, we have two possibilities. So we have 0 and 1 to be transmitted. Now as an output, there can be again two possibilities, one is 0 and another is 1. Now this 1 can be received as 1, or this 1 can be received as 0 also. This 0 can be received as 1 also, and that probability is p, that transition probability is p. Similarly, 1 can be received as 0 with a transition probability of p. So by symmetry, 0 being received as 0 has a probability of 1 minus p. Similarly, 1 being received as 1 has a probability 1 minus p. After that, the discrete input continuous output channel was discussed. So in this, we have discrete input, that is the symbols are discrete. Like suppose we have k symbols, so this should be capital K. Yeah, if we have k symbols, then for k equal to 0 to k minus 1, we have it, and discrete input, and this is a modulated alphabet. Like we'll have finite alphabet, however at the receiver end we'll receive a continuous valued signal. This is the same case that we have in our analysis. Like our received signal can take value from minus infinity to infinity, that is because of our Gaussian noise. So we are basically currently looking at this situation, and this situation is completely characterized by this particular transition probability, that is PDF of y conditioned of what input symbol is being transmitted. Another way or another channel model is this waveform channel, where we transmit and receive continuous waveforms. Both transmission waveforms and reception waveforms can be represented in terms of some finite number of bases or n-dimensional bases, and that's why this waveform channel can be reduced to its equivalent discrete time channel, which can be characterized by this particular PDF. Okay, so this was all that was covered in this particular week. Now if you have any queries, then please let me know. Otherwise, I'll go ahead and start discussing the questions that I have planned today. Okay, if there are no questions, then let's start with the questions that I have planned. So let's start with the first question. So what does it say? Coherent orthogonal binary FSK modulation is used to transmit two equiprobable symbols, S1 equal to alpha cos 2 pi f1t and S2 equal to alpha cos 2 pi f2t. If alpha is equal to 4 millivolts, and let the PST of this additive wide Gaussian noise be n0 by 2, which is equal to 0.5 into 10 raised to minus 4 watt per hertz. Using the optimum receiver, we need to find the bit error rate for this particular constellation scheme, and the data rate that we are using is 500 kilobits per second. So this is the information that is given. So let me just highlight what all things are given. We have binary FSK, and the orthogonal waveforms that are sent are these, and the coefficient alpha is 4 millivolts, and the AWG and PST is this, and we are using an optimum receiver, and we need to find the bit error rate, and the data rate is given as 500 kilobits per second. So these are the things that we have. Now in the class we had seen that this any orthogonal signaling, if it is binary, then we'll have two vectors which will be something like this. Let's say this corresponds to S1 and this corresponds to S2. Or since we are sending one bit at a time, this ES is equal to EB. So this we have seen in the class, like the component of this won't be available here or won't be available in second, because these two are orthogonal. So these are the cases that's given here. Okay, now one more thing that we had seen in class was for a binary scheme. For a binary scheme, the probability of error depends on the minimum distance between these two constellation points. So this probability of error can be completely given by this minimum distance, which is given as q of t minimum square whole divided by 2 N naught. So this also we had seen earlier. Now what is the minimum Euclidean distance between these 2 points? So this d min square is basically EB plus EB, that is equal to 2EB. Sorry, this is not square. Yeah. Yeah. So therefore, this probability of error, we can write it as Q function of under root of d mean square whole divided by under root 2 N naught, which is equal to Q function of under root 2EB by 2 N naught which is basically, this is equal to Q function of under root EB by N naught. So this is what we are having. Let's say this is equation 1. So we know the value of N naught from here. We know the value of N naught from this given quantity. However, what we need to find is this EB. So what we don't know is what is the value of this EB. So by definition, this EB is equal to the energy of this signal as well as energy of this signal. Okay, so let's try to find out that. So what we need to find is EB, and EB is energy of any of these two signals, S1T and S2T. And one more thing we should note is this S1T and S2T are sent only for a one symbol duration. So this S1T and S2T sent for one symbol duration only. Okay, so now let's say let T equal to symbol duration therefore EB is equal to integral 0 to T S1 square T dt, which is equal to integral 0 to T alpha square cos square 2 pi f1 t dt. So this comes out to be as integral 0 to T alpha square, this cos square 2 pi f1t I can write as 1 plus cos 4 pi f1t by 2 dt, which is equal to integral 0 to T alpha square by 2 dt plus integral 0 to T alpha square cos 4 pi f1t by 2 dt. Now generally these f1s are some integer multiples of t, or these f1s are very large, so this integral can be considered as 0. So what we are left with is only the first integral, which evaluates as alpha square t by 2. So what we are having is EB is equal to alpha square t by 2. This we have. Now alpha square is given, we don't know what is t. This alpha square, or rather alpha, is given as 4 millivolts. So if we look here, this alpha is given as 4 millivolts, but we don't know what is the value of t. However, we are given something which depends on symbol rate, which is this data rate, which is 500 kilobits per second. So what we are having is data rate, which is equal to k by t is equal to 500 kilobits per second. Now we are having binary transmission, like binary FSK, which means that this k is equal to 1. So therefore we have 1 by t is equal to 500 into 10 raised to 3 per second, which implies that this t is equal to 1 upon 500 into 10 raised to 3 seconds, which is equal to 2 into 10 raised to minus 6 seconds. So now we have these values. So therefore this EB, if we substitute whatever we have obtained here in the equation here, so what we have is this alpha square is 4 millivolts, that is 4 into 10 raised to minus 3 square multiplied by 2 into 10 raised to minus 6, which is equal to 16 into 2 into 10 raised to upon 2. So this 2 gets cancelled, forgot, yeah, into 10 raised to minus 12. So this is the value of EB that we are having here. So therefore if we get back to what we have derived in our equation 1, this probability of error is q function of under root EB by n naught. So let's substitute it here. So from equation 1, probability of error is equal to q function of under root EB by n naught, which is equal to q function of under root of 16 into 10 raised to minus 12. This is the EB that we have. Now let's go back and look at what is the value of n naught. So this n naught by 2 is equal to 0.5 into 10 raised to minus 12. So this n naught will be 2 into 0.5, which is 1 into 10 raised to minus 12. So this n naught will be basically equal to 10 raised to minus 12. So that we are having here. So this is 1 into 10 raised to minus 12. So these two terms get cancelled. So therefore this probability of error is equal to q function of under root 16, which is equal to q function of 4. So this is the probability of error that we are having for our given system. Any questions? Okay, if there are no questions, then let's go ahead and solve the next question that we are having. Yeah, let us look at the question number 2. So what it says is, consider the 4 PSK and 8 PSK constellations as shown below, and we need to determine the additional energy required by this 8 PSK to obtain the same probability of error. And we had seen that the probability of error largely dominated by the minimum distance or the minimum Euclidean distance. So it is sufficient to know what is the additional amount of energy that we require to so that uh, the minimum Euclidean distance between these two constellations is same. Okay, So for that, what we'll do is the Euclidean distance, or the minimum Euclidean distance, is basically the distance between the two adjacent points. So let's say this is D. Similarly, the Euclidean distance for these two, for this constellation, will be the points between these two. So let's say this is T2 and this is T1. So for same probability of error, let's say approximately, we need D1 equal to D2 equal to, let's say, D. Okay, so this is what we require. Okay, now now this is a PSK constellation, and any point at this PSK constellation is basically, this point is basically under root E comma 0, let's say E2, and this is also 0 comma under root E2. So basically the radius of for this PSK constellation is given by under root of the energy of this PSK constellation. Similarly, this thing will be energy E1 of this PSK constellation. Why is it so? Because for PSK with average symbol energy E, the constellation points are under root E cos theta m comma under root E sin theta m. So this is a standard thing that we know, and this is valid for any PSK, any M array PSK constellation. Okay, so if that is so, what we need to find is, we need to know what is the additional energy that we require for having same probability of error. So basically we want E2, or let's say E1 by E2. This is what we want, and therefore this will be equal to, this under root E1 is equal to R1, and therefore E1 will be equal to R1 square and E2 will be equal to R2 square. So this is what we are having. Okay, so we need to find this. So let us find what are the radius. I'll add same thing here. So let us first find out the value of R2. Okay, so now this is R2. This is R2. This is also R2. And this thing is D. So what we have is, by Pythagoras, theorem, D square is equal to R2 square plus R2 square, that is 2R2 square, which means that R2 square is equal to D square by 2. So this is what we are having for the first thing. Now let us look at this equation, this thing. Now this is R, this is R1, this is R1, and this thing is D. This entire thing is D. Now if I drop a perpendicular from this, then this thing, this part will be D by 2, and this will also be D by 2. And another thing you should notice, this entire angle is 45 degrees or pi by 4, which means that this single angle will be pi by 8. Yeah, so this we know by our basic maths. So here in this figure, what we can say is, if we consider sine pi by 8, so that will be equal to this opposite upon hypotenuse, that is d by 2 upon r1. So this is equal to d by 2 upon r1, which implies that this r1 is equal to d upon 2 times sine pi by 8, which again implies that my r1 square is equal to d square upon 4 sine square pi by 8. So this we know. Therefore, what we have is E1 by E2 is equal to R1 square upon R2 square. So that is equal to D square upon 4 sine square pi by 8 upon D square by 2, which comes out to be 2 upon 4 sine square pi by 8, which is equal to 1 by 2 sine square pi by 8. So this is what we are having here. Just a moment. Yeah, so this is what we are having. And yeah, and this approximately comes out to be 3.4. So 3.4 times higher energy we will need. So what does this mean? To just take this entire thing a little bit upwards and remove this. Okay, so this means that we need approximately 3.4 times higher energy than 4 psk for same probability of error or same Euclidean or same minimum Euclidean distance. Any questions? Okay, if there are no questions, then let us go ahead and see the question 3. So what we need to find here is, let us consider the following 4-point constellations Now the question is, as a designer, if you are designing a particular constellation scheme, or you have been asked to design a particular constellation scheme, which of the following two will you pick as a designer? And in order to do that, what all things should we look at? So we should look at the minimum distance, the average power, and the PAPR. Okay, so what does that mean? How to characterize it? By observing these two quantities. So for that, we want higher minimum distance, we want low average power, and we want low PAPR, that is low peak to average power, low PAPR, or PAPR should be close to 1. So these are the things that we want here. Okay. Okay, so this is what we are having. Okay. So now let us consider the first constellation scheme here. So what, let's say this is figure 1. So for this particular figure, this constellation point has coordinates. So if I drop a perpendicular from here, these are equidistant, so this will be minus under root a. So this is minus root 2a comma root 2a. And similarly, this point will be minus root 2a comma minus root 2a. This point is minus 2 root 2a comma 0, and this point is 0 comma 0. So this we have here. Okay. So now the minimum distance will be between these 2 points. These are the closest. So this is d min, let's say 1. So d min 1 is basically distance between these 2 points. So, or let's say d min square. So this d min square is equal to 2a square plus 2a square, which is 4a square, which means that d min 1 is 2a. Next thing that we need to look at is the average energy or the average power that we are having. So we have this average, and let us say that all of these points are equiprobable. So that will be power of this point plus power of this point plus power of this point plus power of this point whole divided by 4. So the power of first point is 0, this point is 0. The power of this point will be 2a square plus 2a square, which is 4a square, plus power of this point will be the square of this quantity, that is 4 into 2, 8a square, plus power of this quantity, so that will also be equal to 4a square, that is 2a square plus 2a square, which is 4a square whole divided by 4. So this is equal to 16a square by 4, which is equal to 4a square. And next thing that we need to do is we need to find PAPR. And if you observe carefully, the highest power is this 8a square, which corresponds to this particular constellation. So the peak power that we have is this 8a square, and the average power that we have is this 4a square. And PAPR is basically ratio of this peak power by this average power. So this PAPR is equal to 8a square upon 4a square, which is equal to 2, which is definitely twice, or which is definitely higher than 1. So this is what we are having here. This is for constellation 1. Now let us do a similar thing for the second constellation. So for this figure 2, our second constellation, this point is a comma 0, this point is 0 comma a, this point is minus a comma 0, this point is 0 comma minus a. And again, the minimum distance will be the distance between these 2 points. Let's say this is d min 2. Okay, so therefore this d min 2 will be equal to under root of a square plus a square, which comes out to be under root 2a square, which is equal to root 2a. Now let us find out the average energy, that is E average. We have it here itself. So that will be equal to energy of this point plus energy of this point plus energy of this point plus energy of this point. So energy of this point is simply a square. Similarly, energy of this point is a square. Energy of this point is also a square, and this point is also a square. So what we have is a square plus a square plus a square plus a square whole divided by 4, which is equal to a square, which implies that the PAPR is equal to a square, which is the peak power. All of these constellation points have same power, which is equal to a square, and the average power also comes out to be a square upon a square, which is equal to 1. So this is what we are having. We are getting a good PAPR, we are getting less in average energy, but also we are getting higher value of d min, a lower value of d min, which means that I'll have a higher probability of error compared to this previous constellation. Now if my as a designer, if I am given conditions that my PAPR should be equal to 1 and I should not exceed, or I should not have a huge amount of energy consumed, and the probability of error constraints are satisfied, then I can go with this particular constellation. But if I can burn more energy, if I can compromise with this PAPR, which may not be the case every time, which may not be the case, which may not be a favorable case, then even if I'm having a significantly lower probability of error, still I may not be able to go, and I'm sorry, if I'm able to burn higher amount of energy and I can compromise little bit with my PAPR, then I can go for this particular constellation, because it gives a higher minimum distance compared to this. But again, it requires 4 times more energy on an average, which is significantly higher. Any questions? Okay, if there are no questions, then let's go ahead and look at the 4th question. So what does it say? It says that consider a signal detector with input R equal to plus minus A plus N, where this plus minus A are the symbols that are transmuted and these are equiprobable, and this N is Laplacian noise, and the probability density function, or the PDF of this noise, is given as like this. Now what we need to do is we need to determine the probability of error for this particular given setup. So this is the question that we are having. Now if you want to find the probability of error, so that probability of error should correspond to some particular decision rule. Okay, so what we need to do is, first thing is we need to derive optimal decision rule, which is map, or it is if equiprobable, or let me write it in this form, which is equal to ml if equiprobable symbols. Okay, we need to do this first. And after that, we need to find probability of error. Now in our given setup, it is given that we have equiprobable events. So we know that probability of A is equal to probability of minus A, which is equal to 1 by 2, and this is given to us. Okay, and now let us, which means that we can go for ML rule or maximum likelihood rule. So for that we need to find the likelihood functions. So what does this ML rule say? So this ML rule says that if PDF of R given A is transmitted is greater than PDF of R given minus A being transmitted, then I'll decide in favor of A. If PDF of R given A is less than PDF of R given minus A, then I'll decide in favor of minus A. So this is what the ML rule is telling us. Now let us find these two functions. Okay, so what we have is, let's say first thing, A is transmitted. That means we need to find probability of R given A. So what we should receive is, this R will be equal to A plus N, which means that N is equal to R minus A. Therefore, this probability of R given A is equal to this PDF of R given A is equal to PDF of this noise evaluated at R minus A. Now PDF of noise is given as this, so what we have here is this is equal to 1 upon under root 2 sigma e power minus mod R minus A root 2 by sigma. So this is PDF of R given A. Now in similar way, let's say minus A is transmitted. Which means that we need to find PDF of R given minus A. This we need to find. So what we will be receiving is, minus A was sent, so we'll receive minus A plus some noise, which means that my noise N is equal to R plus A. Therefore, PDF of R given minus A is equal to, now we are is equal to PDF of noise evaluated at R plus A. So this is equal to 1 upon under root 2 sigma e power minus magnitude R plus A root 2 by sigma. Now here the assumptions that we are making is, these two quantities are independent, which is a general assumption that noise is independent of what we are transmitting. And yeah, and another assumption that I forgot to mention here is this A is non-negative or is positive. Okay, So this is what we are having. So now let us plug in what we are having in our ML rule. So let me take this maximum likelihood here. Okay, so this is what we are having. So probability of R given A is this quantity. So I'll just take it also there. And probability of R given minus A is this quantity. Yeah. This is what we are having. Now these two factors, 1 upon under root 2 sigma and 1 upon under root 2 sigma, are positive quantities, so I can just ignore them. So I can cancel these two out, and let's take log on both sides. Now as log is monotonically increasing function, so this log looks something like this. This is log function. So if I take log on both the sides, then the inequalities won't be flipped. They would remain same. So if I take log, then this will be equal to minus r minus of magnitude r under root 2 by sigma is greater than or equal to a minus a minus magnitude r plus a under root 2 by sigma. Again, these two quantities are positive, so I can cancel them out. And I can take this quantity on left hand side. So what we are having is magnitude r plus a minus magnitude r minus a, like this. So this is the decision rule that we are having here. And now let us try to evaluate this decision rule of what we are having. So I'll take this. Yeah, and let me just reduce its size. Yeah. So this is what we are having here. Now look at these things. Just look at this r plus a. Now this r plus a is equal to minus of r plus a if r is less than minus a. It is equal to r plus a if r is greater than or equal to a. Okay. Similarly, if we look at this, then this is equal to minus of r minus a if r is less than a. This is equal to r minus a if r is greater than or equal to a. This is minus sign here, sorry. Yeah, so this is what we are having. So let us try to understand what's happening here. So let's say this is r, this is 0, this is minus a, this is a. Okay, so if we look at this region, then in this region, this is a region where r is less than minus a. Now in this region, what do we have? We have r plus a, magnitude r plus a as this, and magnitude r minus a as this. So we have, let me write it like this. So in this first region, we have this as now let us look at this region. Which is this region? This region is basically r greater than or equal to a. Like r greater than or equal to a means this region, r greater than or equal to a. And in this region, this r will also be greater than or equal to minus a, which means magnitude r plus a is equal to r plus a. And similarly, magnitude r minus a will be equal to r plus a. So here This will be equal to r plus a, and this will also be equal to r minus a. Now if we consider this region, now in this region here r is lying between minus a and a, means r is greater than or equal to minus a, which means magnitude r plus a is equal to r plus a. So here we have it as r plus a. Yeah, so this is greater than or equal to minus a. However, it is less than a. So if it is less than a, then magnitude r minus a will be equal to minus of r plus a. So this quantity, let me use a different color. Yeah. So this will be equal to minus of r minus a. So this is what we are having. Now let us consider this decision rule that we are having. So how many regions do we have? We have 3 regions. So I'll also take this figure. This figure also on the next page so that it's easy to understand what's happening. I'll reduce its size. Yeah, so this we are having. So let us consider, I'll just divide this page in 3 parts. So for first region, this is second region and this is third region. Okay, so for this first region, let us look at the decision rule. So for this first region, I'll have to replace this quantity by minus r plus a, minus of r plus a, and this quantity as minus of r minus a. So this comes out to be minus of r plus a, minus of r minus a. So minus minus becomes plus. So this is r minus a. So in that case, what do we have here is this r. This is minus r. This is minus r and this is r. So these two get cancelled. So what we are left with is, minus a, which is equal to minus 2a. Now this quantity here, since a is positive, since a is greater than 0, this quantity here minus 2a is less than 0 always, which means that decide as minus a. When to decide as minus a? When r is less than minus a. So this is what we have. Now let us consider the third region. So in third region, we need to replace this r plus a, magnitude r plus a as r plus a, and magnitude r minus a as r minus a. So therefore what we have is r plus a minus of r minus a is greater than 0 than a, and less than 0 than minus a. Again this is r and this is minus r, so we can just cancel them out. So these two get cancelled, and what we have is 2a is greater than 0 than a and less than 0 than minus a. Now same argument will hold, that since a is greater than 0, then 2a will also be greater than 0 always, which means that decide as a when r is greater than a. So this we have here. Now let us consider the second region, that is the region, this middle region that we are having. So in this situation, we need to replace this quantity magnitude r plus a with r plus a. However, this quantity has to be replaced with minus of r plus a. So what we have is r plus a minus minus plus r minus a, like this. So we have 2r and r. So if r is greater than 0, then we decide in favor of a, or let's say greater than or equal to 0, and if r is less than 0, then we decide in favor of minus a. Okay, so this is what we have. Now if we combine these three things that we have obtained here, these three things, when r is less than minus a, then we are deciding in favor of minus a. Again, when we are between minus a to 0, we are deciding in favor of minus a. So which means that whenever my r is less than 0, I'll decide in favor of minus a. Similarly, when r is greater than or equal to a, we are deciding in favor of a. Also, when my r is greater than a, or when my r is between 0 to a and a to infinity, then we are again deciding in favor of a. So in other words, we can simply say that if my r is greater than a, then I'll decide in favor of a itself. So by combining these three arguments which we have here, so let me write it properly. Therefore, combining the arguments made for the three regions, we conclude that if r is greater than 0, then decide in favor of a. If r is less than 0, then decide in favor of minus a. Now let us visualize what is happening with the help of the PDF. Now one should note that the Laplacian PDF looks something like this. So this is the Laplacian PDF. Now this PDF is shifted to plus a and minus a for the respective cases. So let us try to understand what is happening. So let's see, this is minus a, this is plus a, and just take it. Yeah, like this. So this thing here is PDF of r given minus a being transmitted. Similarly, yeah, this is PDF of r given a being transmitted. So this is what we are having. Now the threshold that we have is 0. So this is our decision threshold. This is 0. This is our decision threshold. And this yellow thing, or let me write it in this way. So this is region for minus a, and this is this thing here is region of, or rather region for deciding in favor of A. This is what we are having. Okay. Now we know the decision rule. Now what we need to do is, what our original aim was, what does the question ask? The question needs us to find the probability of error. What we have found out is we have derived the optimal decision rule. We have finished with the first part. And now what we need to do is we need to find the probability of error. We need to find the probability of error for this particular decision rule. So now let us try to do that. Yeah. So this is what we have. Now, when will an error occur? An error will occur when we are transmitting A but we are detecting minus A. That is, an error will occur if we are transmitting A. We are basically transmitting A but we are receiving minus A. That is, we are in this region. So when an error will occur given A transmission will be basically this region. This region. So this thing is probability of error given A being transmitted. Similarly, this region will be probability of error given minus A being transmitted. Now by symmetry, these two are very symmetric. So by symmetry, probability of error given A being transmitted is equal to probability of error given minus A being transmitted. Therefore, probability of error will be equal to probability of A, which is 1 by 2, into probability of error given A plus 1 by 2 probability of error given minus A, which is equal to probability of error given, let's do it for minus A. Let us solve this integral. Okay, so what we need to find is, therefore, probability of error given minus A is being transmitted is basically defined as Z0, or let's say Z of minus A. Z of minus A means it is region where we detect as minus A, and this is equal to Z of A. But when will an error occur? So when I have received R in that region given A being transmitted, so that will be equal to PDF that R given A dr, or this R lies in this region. So this is the probability of error given minus A is transmitted minus A. And sorry, made a mistake here. Yeah. So PDF given R given minus A, that I have transmitted minus A. However, this R which I am receiving lies in this region ZA. So I will have to integrate this PDF over the region of A. So this is the probability of error given minus A. So therefore, probability of error given minus A is equal to, now this region ZA is basically a region from 0 to infinity. So this is integral 0 to infinity, and then we need to substitute PDF of R given A, and PDF of R given A was 1 upon under root 2 sigma e to the power minus magnitude R plus A root 2 by sigma dr. Now this quantity, we have seen these regions like this R plus A is positive for this region entirely. We know this, that this R plus A is equal to R plus A when R is greater than or equal to minus A, and we are integrating over this region, and over this region this R plus A is always positive, so I can simply ignore the mod. So I can, if I do that, then this is equal to, you can take this constant out as well. So this is under root 2 sigma integral 0 to infinity e power minus r root 2 by sigma into e power minus a root 2 by sigma dr. This particular quantity is constant, I can take it outside. So this is equal to 1 upon root 2 sigma into e power minus a root 2 by sigma, and integral of this e power minus r root 2 by sigma is equal to e power minus r root 2 by sigma upon minus root 2 by sigma, and this thing is integrated over 0 to infinity. Now this sigma and this sigma gets cancelled, and this root 2 and this root 2 in total correspond to 1 by 2 into e power minus a root 2 by sigma. E power minus infinity is 0, minus 1 upon minus 1. So this comes out to be 1 by 2 into e power minus a root 2 by sigma. And by the argument which we have made earlier, this probability of error is equal to probability of error given minus a was transmitted. So this comes out to be probability of error also. Any questions in this particular part? Okay, if there are no questions, then let's go ahead and look at the next question that I have to take. Now, this question, the decision rule part of this particular question was covered in previous tutorial as well. So I'll quickly take that part also, but now this will majorly focus on how do we find the probability of error, the minimum probability of error. So what is given is a source emits 0 and 1 with probabilities 1 by 3 and 2 by 3 respectively, and the emitted bits are communicated to the receiver, and the receiver decides on 0 and 1 based on R. Now we need to find the minimum probability of error if the likelihood functions are given like this. Now we had seen that we'll achieve minimum probability of error if we go for the optimal decision rule, and that optimal decision rule is basically maximum a posteriori probability, which is basically map rule. So we'll achieve this minimum thing when we are going for a map rule, or basically map rule. So optimal decision rule is basically f of r given 1 into probability of 1, if that is greater than f of r given 0 into probability of 0, then decide in favor of 1, otherwise decide in favor of 0. So this we know. Now probability of 1 is 2 by 3 and probability of 0 is 1 by 3. So probability of 1 is 2 by 3, so this is 2 by 3 into f of r given 1 into 1 by 3 f of r given 0. So now let us look at these two quantities individually. So let us look at 2 by 3 into f of r given 1. So this is equal to 2 by 3 into 1 by 6. So 2 by 3 into 1 by 6 will come out to be 1 by 9. So this is equal to 1 by 9 if my r lies between minus 1 and 5. And this is equal to 0 otherwise. Similarly, 1 by 3 f of r given 0 is equal to 1 by 3 into f of r given 0, so that will be 1 by 3 into 1 by 4, which is 1 by 12, and that will be valid when we are between minus 3 and 1. So this is equal to 1 by 12 if we are between minus 3 and 1, it is 0 otherwise. So the situation that we have ended with is something like this. This is r, this is some axis, let's say this is 0, 1, 2, 3, 4, 5, minus 1, minus 2 and minus 3, like this. Then this thing 1 by 9, that is 12, 2 by 3 f of r given 1, this is 1 by 9 for minus 1 to 5. So let's say this is 1 by 9. So we have a situation like this. So this thing is 2 by 3 f of r given 1, and we have 1 by 3 r given 0 as 1 by 12. So let's say this is 1 by 12, and this is valid for minus 3 to 1. Like this. So this thing is 1 by 3 f of r given 0. So this is what we are having here. So now we need to look at the region wherever these quantities are higher. So if we look carefully, then in this region we have 2 by 3 f of r given 1 greater than 1 by 3 f of r given 0, which means we need to decide 1. However, if we look at this region, then in this region we have 1 by 3 f of r given 0 greater than 2 by 3 f of r given 1, which means decide 0. So what do we have is, if r belongs to minus 3 to 1, decide as 0. However, if minus 1, sorry, and if r lies between minus 1 to 5, decide as 1. So now what we need to find is probability of error is equal to probability that 0 was transmitted into probability of error given 0 being transmitted plus probability of 1 into probability of error given 1 is transmitted. Okay, so now let us solve. So we know that probability of 0 is 1 by 3, so this comes out to be 1 by 3 probability of error given 0 plus probability of 1 is 2 by 3 into probability of error given 1. Okay, so now let us look at this. Yeah. So let us see this probability of error given 0. So basically we need to integrate PDF of r given 0 being transmitted over the region where we decide as 1, that is in this region, that is from minus 1 to 5 dr. Now let us see the region of minus 1 to 5. So from minus 1 to 5, region -1 to 5, -1 to 5. In this, the only overlap is the region from -1 to 1, and in this region your f of r given 0, f of r given 0 is equal to 3 times 1 by 12, that is 1 by 4, that is this quantity. So in this region, so this is equal to, okay, take notations that we are having. So this is valid only for the region of -1 to 1, and in this region f of r given 0 is 1 by 4 dr, which comes out to be 1 by 4 into 2, which is 1 by 2. Now let us find probability of error given 1 being transmitted. So that will be, we'll have to integrate the PDF of r given 1 over a region where we decide it as 0. So that is -3 to 1. So this is -3 to 1. Now let us see that region. So that region is this, -3 to 1, this region. Now in this region, the PDF of r given 1 is 0. Your PDF of r given 1 lies here. However, we want to integrate in this region. So there is no overlap, which means that if outside that particular region or the region where we want to integrate, this particular quantity is 0. This quantity is 0. So this is 0. Therefore, probability of error is equal to 1 by 3 into 1 by 2, which comes out to be equal to 1 by 6. Now such kind of questions are asked in GATE exam, like this particular question and the one I'll take after this, or all the questions that I'm going to take after this, mostly maximum times those have been asked in GATE exam. So this kind of analysis is useful, and yeah, it gives you better understanding of how to find probability of error. So that's why I'm taking these particular examples, because once you know the formula you can just substitute the values. However, understanding such kind of basics is more important, so that if you forget the formula on spot you can work out quickly. Any questions? Okay, if there are no questions, then I'll move ahead with the next question. Yeah, so there is a small error in this. This is not 1. This is 0.2. Yeah. So what we have is consider a binary digital communication system with equally likely zeros and ones. So when 0 is transmitted, the output that the receiver sees lies between -2.5 to 2.5. So what we have is f of, or let's say t of r given 0 is equal to, so this lies between -2.5 volt to 2.5 with equal probability, which means that this is a uniform distribution. So if it is lying between this range, then the probability mass or probability density at each and every value will be simply 1 upon 0.25 minus 0.25. So that will be equal to 1 upon 0.5, which is equal to 2, and this is equal to 0 otherwise. So let me write it in short here. This is equal to 1 upon 0.25 minus of -0.25. So this is uniform distribution. The next thing that is given is when 1 is transmitted, the detector observes any value between 0 and 1. Any value it will observe between 0 and 1. So probability of r given 1 is equal to 1 if r lies between like this. Okay, so something like this is happening. It is 0 otherwise. Okay, so the detector threshold is 0.2. So what does that mean? If r is greater than 0.2, then decide in favor of 1. If it is less than 0.2, then decide in favor of 2. This is the decision rule that is given. And what we need to do is we need to find the probability of error. And again we are given that the zeros and 1 occur with equal probability. Okay, so the 0 and 1 are equiprobable. So if the zeros and 1 are equiprobable, then this probability of error is basically equal to probability of 0, which is 1 by 2, into probability of error given 1 being 0 being transmitted, plus 1 by 2 into probability of error given 0 being transmitted. 1 being transmitted. So let us find these two quantities. So this probability of error given 0 being transmitted is given as integral over the decision region of 1. So what do we need to integrate is PDF of R given 0 over the decision region of 1, and decision region of 1 is R greater than 0.2. So this is R greater than 0.2. So if R is greater than 0.2, then the decision region, so this R given 0 just lies between minus 0.25 to 0.25, and we are integrating for R greater than 2, greater than or equal to 2. So we'll just integrate it over 0.2 to 0.25. So this is equal to integrating over a region of 0.2 to 0.25, and this PDF of R given 0. So the PDF of R given 0 in this particular region is 2, otherwise it's 0. So we have 2 dr. So this is equal to 2 multiplied by 0.25 minus 0.2, which is equal to 2 multiplied by 0.05, which is equal to 0.1. Okay, now let us find out what is probability of error given 1. So that will be basically integrating PDF of R given 1 being transmitted and over a region where we detect 0, and for that we have this R should be greater than 0.2, or let's say R less than equal to 0.2. So this will be equal to, now this PDF of R given 1 lies between 0 to 1. Okay, so now what we are integrating is over a region where R is less than 0.2. So this will be non-zero only when we are integrating for over a region of 0 to 0.2. So this is 0 to 0.2 multiplied by 1 dr. So this comes out to be equal to 0.2. Okay. Therefore, probability of error is equal to half into 0.1 plus half into 0.2, which is equal to half into 0.1 plus 0.2, that is 0.3, which is equal to 0.15. This is the probability of error that we are having. Any questions? Okay, if there are no questions, then let us go ahead and look at the next question. So the next question says that we have a binary symmetric channel, and this has a transition probability of 1 by 8. If probability that X is being transmitted, then we need to find the probability of error. So what is given is we have a binary symmetric channel. Okay, so this is 0, this is 1, this is X. We're having Y, so we can either receive 0 or receive 1. And the transition probability that 0 being received as 1 is given as 1 by 8, which means that this X being received as like 0 being received at 0 will be 1 minus 1 by 8, that is 7 by 8. Similarly, 1 being received as 0 has probability 1 by 8, which means that 1 being received as 1 will have probability 7 by 8. So what we are having is PDF of y equal to PMF of y equal to 0 given x equal to 0 equal to, or rather x equal to 1 is equal to 1 by 8. Similarly, PMF of y given 1 x equal to 0 is equal to 1 by 8. Okay, therefore also what we have been given is probability of transmitting 0 is 0.9 and probability of transmitting 1 will be 1 minus 0.9, which is 0.1. Therefore probability of error is equal to probability that x is equal to 0 into probability of error given, or rather it will be probability that we are receiving 1 when x is transmitted plus probability of x equal to 1 multiplied by probability that y equal to 0 given x equal to 1 was transmitted. So probability of x equal to 0 is 0.9 into probability of y given x equal to probability y given y equal to 1 given x equal to 0 is 1 by 8 plus probability of x equal to 1, which is 0.1, multiplied by probability that y equal to 0 given x equal to 1, which is again 1 by 8. So this comes out to be 1 by 8. So this is 1 by 8 multiplied by 0.9 plus 0.1, which is 1. So probability of error is 1 by 8. Any questions? Okay, if there are no questions, then let's see the next question. So what do we have here is input x to a binary symmetric channel is 1 with probability 0.8. So again we are having a binary symmetric channel, so let me just draw it. So this is x, so x can be 0 and 1, so x is equal to 1 with probability 0.8 and x is equal to 0 will be 1 minus 0.8, so that is 0.2, and the crossover probability is 1 by 7, that is 0 being received as 1, that probability is 1 by 7. Similarly, 1 being received as 0 has the same probability 1 by 7. 0 being received as 0 will have probability 6 by 7, and 1 being received as 1 will have then probability 6 by 7. So this is given to us. So let's look what is asked. If the received bit is y, so if the received bit, this y, is equal to 0, then we need to find the conditional probability that 1 was transmitted. Okay, so what we need to find is probability that y equal to, x equal to so we have seen y equal to 0. So after seeing y as 0, what is the probability that the transmitted bit was 1? So that is probability that x equal to 1 given y equal to 0. So now this I can write as probability y equal to 0 given x equal to 1 multiplied by probability that x equal to 1 divided by probability of y equal to 0, and this comes from Bayes rule. Okay, so this we know. Now probability that y equal to 0 given x equal to 1. So probability that y equal to 0 given x equal to 1, which is this transition probability, which is 1 by 7. So therefore probability x equal to 1 given y equal to 0 is equal to 1 by 7 multiplied by probability that x is equal to 1. So this is into 0.8 divided by this p of y. Now this p of y we can write as probability that x equal to 1 into probability that y equal to 0 given x equal to 1 plus probability that x equal to 0 into probability of y equal to 0 given x equal to 0. Okay, so this is law of total probability or total law of probability. So from this probability of y I can write as probability of x equal to 1, which is 0.8 multiplied by y equal to 0 given x equal to 1 probability, then this is 1 by 7 plus 0.2 into 1 by 7. Oh, I'm sorry, into sorry. Yeah, so probability that x equal to 1 is 0.8 multiplied by 1 by 7 plus 0.2 into 6 by 7. So that this is probability that x given by x equal to 1 given y equal to 0. So let's calculate this. So this is 0.8 divided by 7 divided by 0.8 divided by 7 plus 0.2 divided by or multiplied by 6 by 7. So this comes out to be approximately equal to 0.4. Okay, yeah, so this is what we are having. Now the second part of this question says that we need to find the probability of error and the decision threshold, or the optimal decision threshold. So probability of error is actually simple. So that we have done in previous lecture or previous question also. So this probability of error is equal to probability that x equal to 0, which is 0.2 into probability into the crossover probability, that is 1 by 7 plus 0.8 into 1 by 8. So what are these? So this thing is probability that x equal to 0 and this thing is probability that y equal to 0 given y equal to 1 given x equal to 0. Similarly, this thing here is probability that x equal to 1 and this thing here is probability that y equal to 0 given x equal to 1. Okay, so this is what we are finding. So this comes out to be equal to 1 by 7. However, what interesting thing we need to look at is this quantity decision threshold for this binary symmetric channel. So this is something like trivial, which is actually a very trivial thing, but still we'll see what exactly we are having. Basically, y takes only two values. However, still we'll just see what happens. Like this y can be some noisy thing, like y can be 0 and 1. So when should we decide in favor of 0 and when should we decide in favor of 1? Okay, so the optimal decision rule is basically probability that x given y, or rather probability that y given x equal to 0 into probability that x equal to 0 is greater than probability that y given x equal to 1 probability that x equal to 1. So therefore probability that y given x equal to 1 upon probability that y given x equal to 0 is greater than, decide in favor of 1. I have taken this quantity, this quantity here and this quantity here into probability that x equal to 0 upon probability x equal to 1. So probability of x equal to, yeah, okay, fine. So this thing here, probability of x equal to 0 is 0.2 upon probability of x equal to 1 is 0.8, which comes out to be 1 by 4. We should get some trivial answer. Okay, so what we need to check is probability that y given x equal to 1 upon probability of y given x equal to 0, which is greater than 1 by 4. Then decide in favor of 1, otherwise decide in favor of 0. Something like this we are having. Now let's see the cases. Case 1, y equal to 0. So therefore probability of y equal to 0 given x equal to 1 upon probability of y equal to 1 given x equal to 0. So if that is the case, then okay, so this we are having. Now if y equal to 0, okay, if y equal to 0, then what we are having here is this thing is 1 by 7 on 1 by 6. Sorry, 6 by 7, which comes out to be 1 by 6, and this quantity is less than 1 by 4, which means that we should decide in favor of x equal to 0. We decide in favor of 0. Now case 2, y equal to 1, then probability of y equal to 1 given x equal to 0 upon probability of y equal to 1 given x equal to, yeah, so this comes out to be 6 by 7 upon 1 by 7, which is equal to 6. This quantity is greater than 1 by 4, which means decide in favor of 1. Okay, what does it mean? If I am getting y equal to 0, then decide that x equal to 0 was transmitted. However, when y equal to 1, decide in favor of y equal to 1 was being transmitted. Now suppose this 6 by 7 and 1 by 7 are interchanged. If those quantities are interchanged, then these ratios will be flipped every time. In that situation, this quantity, like, what it means is, if this thing is 6 by 7, that means that we are more likely to make an error compared to having a correct decision or looking at a correct value. So in that situation, these two ratios will be interchanged, and then we'll get a completely opposite thing. Like, then we'll get a decision rule where if I observe 0, then I'll decide in favor of 1, and if I observe 1, then I'll decide in favor of 0. So those kind of things can also happen if we have these transition probabilities as ulta, like interchanged. Any questions? Okay, if there are no questions, then let us look at the 9th question that I have planned to cover today. So it says that during transmission over a communication channel, bit errors occur with probability p. If a block of n bits is transmitted, then probability of at most one bit in error is. And also we need to find the probability of error. I missed to write the entire question. If n by 2, like how to define an error here. So define an error if n by 2 bits are in error. Okay, so what we are having here is we are having n bits being transmitted, and in that probability that 0 gets converted to 1 is p, which is also equal to probability that 1 gets converted to 0, which is basically equal to probability of error for bit. This we know, or let's say pb. This is given to us. Like this transition is given to us. Like flip, the probability that a bit will flip is given to us. Now it says that we need to find the probability that at most one bit is in error. So probability that, so let's say so let us do this in general. So let's say k bits are in error. Then what does it mean? It means that any k of these n bits might be in error. Okay, any k of these. So that choice will be given by nck or n choose k. And what is the probability that these many bits will go in error? Each will have a probability of error or probability of flipping as p. So that will be equal to p to the power k. However, remaining will be not and will not be in an error, and that's why that will have a probability as 1 minus p to the power n minus k. So this is a binomial random variable with parameter p and n. So this is binomial with parameter n and p. This is binomial random variable, just an aside. Okay, so this we have. So the first thing that we need to find is if that's the probability that at most one error occur, or at most one bit is in error. So probability that at most one bit in error, so this is equal to probability that 0 bits in error plus probability that 1 bit is in error. That is basically, for this case we have k equal to 0, and for this case we have k equal to 1, and we need to substitute that in this particular equation. So by that what we have is we have this as nck, or rather if no, okay, let me do it properly. nc0 into p to the power 0 into 1 minus p to the power n plus nc1 into p to the power 1 into 1 minus p to the power n minus 1. So this thing here is nc0 is 1, so this is 1 minus p to the power n plus nc1 is n, so that is np into 1 minus p to the power n minus 1. So this is the probability that at most one bit is in error. Okay, and after that what we need to find is we need to find this quantity, probability of error, and the error is defined in this form. And okay, error is defined in this form, and if n by 2 bits are in error, or let's say greater than equal to n by 2 bits are in error. Okay, so this thing can be written as, so probability of error is equal to probability that k greater than or equal to n by 2, and n by 2 is an integer, so that I can write as ceil function of n by 2. Sorry, k is an integer, where this if n is odd, then that n by 2 will be a fraction, so I can take n by n minus 1 by 2, or rather n plus 1 by 2. So for doing that thing we can just write k greater than or equal to 1 bits are in error. Now these are singleton events like k equal to seal n by 2, then k equal to seal n by 2 plus 1. These are singleton events and these are disjoint events. So these are basically simply summation that k equal to n by 2 seal of n by 2 to n nck into p to the power k, or rather let me write it properly, probability that k bits are in error. Now this comes out to be summation k equal to seal function seal of n by 2 to n, and this thing probability that k bits are in error is this quantity. So this is n choose k p to the power k into 1 minus p to the power n minus k. So this is what we are having. So this is what we are having here. Any questions? Okay. If there are no questions, then let us look at the last question that I have planned to cover today. So what does it say? A communication system uses a repetition code of rate 1 by 3. What does a repetition code mean? So it means that if I want to transmit 1, I'll repeat it k number of times if the rate is 1 by k. So if my rate of that repetition code is 1 by 3, then I'll transmit, if I want to transmit 1, I'll transmit 1 1 1. That is, if I want to transmit 1, then this will be 1 1 1. Similarly, if I want to transmit 0, then I'll transmit 0 0 0. Now what will the detector do? The detector will see what are the majority number of or what is the majority bit that I have obtained. For example, if receiver sees 110, then decide 1. If receiver sees 010, then decide 0. Whatever is majority, that the receiver will decide. Okay, now what another thing that it says is that each of this bit, like I have 3 bits being transmitted, each of these bits getting flipped. These get flipped with probability 0.1, that is p equal to 0.1. This we know, and we know that these 0 and 1, that is the symbols 0 and 1, these occur equally likely. So these have probability half. Okay, these things we know. So and what we need to find is we need to find the average probability of error. So this probability of error will be basically probability of 1 into probability of error given 1 being transmitted plus probability of 0 into probability of error given 0 being transmitted. These two are half, so I can write it as half into probability of error given 1 being transmitted plus probability of error given 0 being transmitted. Okay, so now let us find out these two quantities individually. So let's first find out probability of error given 1 being transmitted. So when will the error occur? So this will occur when probability that number of ones is equal to 1 or is equal to 0 given 1 is transmitted. Okay, now we have 1 being transmitted in these 3 places. We are transmitting 1 1 1. and we know that this gets flipped with probability p, and it remains as 1 with probability 1 minus p. This is 0.9 and this is equal to 0.1. This we know. Okay, so this event, that probability that one flips, or one position flips to 1, or 0 positions flip. I'm sorry. Yeah. Okay. So this event that number of ones is 1, that only one bit remains as it is, or none of these bits remain as 1, is disjoint. So this I can write as probability that number of ones is equal to 1 given 1 being transmitted, plus probability that number of zeros, number of ones equal to 0 given 1 being transmitted. So if there is only one 1 in this, then 3C1 possibilities, like any of these 3 possibilities, any of these 3 places it can be present. So that will be 3C1, or it will be simply 3. That can occur in 3 ways. So 3 times. What is the probability that a 1 will remain 1? So that will be 0.9. So 0.9 into 1 to the power 1, and remaining 2 will get converted to 0. So that will have a probability of 0.1 square, plus probability that number of ones is 0, which means that all of these ones are flipped to 0. So that probability will be 0.1 cube. And if we solve that, then this thing comes out to be 0.028. Now similarly, if we have probability of error given 0 being transmitted, so that will be equal to probability that number of zeros is equal to 1, or is equal to 0 given 0 being transmitted. So again, these are disjoint events, so we can write it as number of zeros equal to 1 given 0 being transmitted, plus probability that number of zeros equal to 0 given 0 being transmitted. So we again have a similar situation. We had transmitted 0 0 0, and we are receiving something. So a bit gets flipped to 1 with probability 0.1, and remains as 0 with probability 0.9. So with the same argument, if I have only one 0 in one of these 3 places, so that can happen in 3 ways, and the probability that that particular position or that particular 0 remains 0 or is received as 0 is 0.9, and remaining 2 bits get flipped to 1, and that happens with probability 0.1, so that is into 0.1 square, plus we have all of these zeros converted to 1, so that probability will be 0.1 to the power 3, and that comes out to be, again these two quantities are same, so this comes out to be 0.028. Therefore probability of error is equal to half of this summation, so that will be equal to half of 0.028 plus 0.028, which comes out to be 0.028. So this is the probability of error for this particular repetition code. Any questions at this point? So this is what we wanted to find in this particular question, and these were all the questions that I had planned to cover today. If you have any questions, please let me know. Otherwise, you are free to leave the meeting. Thank you for attending today's session.